Welcome to Space Place tonight. Tonight is our guest speaker night, and I'm pleased to introduce from the UW-Madison Astronomy Department, Dan Rybarczyk. Dan came to Madison from Boston University, where he studied astronomy and physics, and he's working on his PhD in astronomy here on a subject that goes way back in Wisconsin astronomy, and that is the interstellar medium, which was a specialty here very early in the 1930s at the University of Wisconsin. So tonight, Dan is going to talk about the earliest stages of star formation and connect that back to interstellar medium studies for us. So join me in welcoming Dan tonight.
All right, thank you, Jim. Can everybody hear me? All right, great. So, as Jim said, I'm going to be talking about the earliest stages of star formation, but my talk really isn't going to be focused on stars. It's going to be focused on the interstellar medium, which is the gas and dust between stars, and that's the place where stars are born. So, can anybody tell me what this is? It's a galaxy, yes. So, the universe is filled with galaxies like this one. There's actually as many as a few trillion galaxies in the observable universe. And one of the goals in studying galaxies is to understand how, in a global context, the sun and the Earth and us came to be. So because we live in a galaxy, so what's our galaxy called? The Milky Way, yes. So we live in the Milky Way galaxy. That means that uncovering the origin of everything around us lies in understanding how galaxies live and evolve. So in order to do that, we have to study the different parts of galaxies. And one of the most important parts of galaxies is stars. So in this image, we can see sites of recent and ongoing star formation. So all of these bright red circles, I've shown an example here, but you can see they're spread throughout the galaxy. So these are regions where young massive stars are forming. We call them H2 regions. Now, the stars that form H2 regions are much larger than the sun, but we can also study how all different types of stars form in our galaxy and in other galaxies, and then we can discern how the sun and the Earth and us formed. So I'm actually going to start with stars and then work my way backwards so we can understand the earliest stages of star formation in the interstellar medium, which is what I work on. So let's talk about how stars form. So stars are important to the structure and evolution of galaxies, as well as the origin of life on Earth. So this really is a very important area of study in astronomy. And here is our general picture of how stars form. So this has been pieced together through observations and through just the study of physics over a long period of time. And we have this sequential structure, this sequence of star formation. So we start with this multi-step process. So in galaxies, there exist these cold, dense clouds of gas and dust that we call molecular clouds. Certain regions of molecular clouds are more dense than other regions. So we call these regions clumps. Then within a clump, you have yet denser, yet smaller regions that are known as cores. These cores can gravitationally collapse and form what we call a protoplanetary disk. So this is a flat, swirling disk that will go on to form a solar system. Overdensities, so clumps within the disk, will actually accumulate mass and go on to form planets like the Earth. And the bright clump at the center is what will become the star of the solar system. Okay, so this is a nice picture, and it tells us kind of the story of star formation. But we're trying to piece together the whole story of star formation. And in this picture, we are already beginning with the existence of molecular clouds. But this merely begs the question, where do molecular clouds come from? So where do these places where stars are born come from in the first place? So let's talk about molecular clouds. There's actually been some really wonderful and revealing work studying molecular clouds in just the past couple of years. And it is entirely changing the way that we view the structure of the Milky Way galaxy, quite literally. So we now, for the first time, have three-dimensional maps of large chunks of the galaxy, which tell us how molecular clouds are structured and provide clues to their formation, telling us where these birthplaces of stars come from. Specifically, we're now learning that many prominent molecular clouds are on the surface of giant bubbles blown into the galaxy by exploding stars, called supernovae. So before we get to that, I actually want to tell you about how these maps are made in the first place, because it's a pretty interesting process. So we've already said that we know stars form in molecular clouds. But one of the problems with studying molecular clouds is that when we look up in the sky, we have no idea how far away these molecular clouds are or how they're structured along our line of sight. So look at this cloud here. If I gave you this picture, or if I took you up to Washburn Observatory and pointed the telescope at this cloud and asked you, how far away is this? Do you have any idea? What if instead I asked you to tell me what this cloud looks like in 3D? So is this cloud a thin sheet that we're viewing face on, or is it a long tube, 100 times longer than it is wide? Would you have any way of telling? Well, really, we don't know. So we don't know by looking at a 2D image of something that exists out there in 3 dimensions. But for most of the history of astronomy, this is all we've had. We've only been able to look at 2-dimensional structure of clouds and speculate about their distance. So this is a really severe limitation to our understanding of how stars and planets form. So without knowing their distance and morphology, it's hard to know how molecular clouds, the birthplaces of stars and planets, fit into the galaxy. Remember, we started by looking at a galaxy. It's hard to know how molecular clouds fit into the galaxy without knowing their distances or shapes. So, what can we do? Well, it turns out that we can now look at stars themselves to figure out the distances to clouds. So, thanks to differences between stars and molecular clouds, as well as some advancements in precision measurements, we can now measure the distances to stars. Not to molecular clouds, but to stars. But we can study some properties of the stars in the direction of molecular clouds to figure out how far away they are and how they're structured. So let's see what that looks like. So now I'm showing you a very cartoonish representation of some stars in the direction of this cloud that I had you look at earlier. So keep in mind, this is a cartoon, but it's actually pretty illustrative of what we actually observe. So there are tons of stars in the Milky Way, including in the direction of molecular clouds. So if this is what we see when we look up at the sky, we see these stars in the direction of the molecular cloud. Imagine now that I tell you that these stars are all the same kind of star, and that in principle, every one of these stars should have a characteristically blue color. You don't need your PhD in astronomy to figure out that something's not quite right here then. Clearly, some of these stars are a lot redder than they should be. But remember, I said nowadays we can measure the distances to these stars. So let's take a look at how this change in color depends on the distance to each star. So we know the distances to these stars. We also know what they should look like. So in principle, they should all have this blue color that the stars down here have. But when we look at particular stars in the direction of this molecular cloud, we find that some of them are much redder than expected. And we can actually measure exactly how much redder they are. We use a quantity that is literally called the reddening to do this. So that's what I'm showing on the y-axis here. So points that are higher up are more red compared to our expectations than the points that are lower down. So if we look now at the reddening, so how much redder these stars look versus distance, we find that stars that are beyond a certain distance, so remember the distance is on the x-axis, so the points here are farther away. Stars beyond a certain distance are a lot redder than the stars nearby. So I'm showing you here the example from the stars in our previous image, which is just, again, this cartoonish illustration. But behind that is real data, so you can see that it actually does follow this trend in reality. So, dust in interstellar clouds tends to make light look redder. It actually filters out blue light, which leaves just behind the red light. It's actually similar to the phenomenon that we see every night and every morning when the sun is low on the horizon. So there the sun's light gets scattered by dust in the atmosphere of Earth and then looks redder. So the same thing happens in interstellar space. Light that passes through dust looks redder. So now, when we look here, we see that only the stars beyond a certain distance have had this large amount of reddening happening. So this tells us that their light has passed through a large quantity of dust that the light from the nearer stars hasn't. And voila, molecular clouds have lots of dust. And the presence of a molecular cloud at this distance can account for why these stars look so much redder than these stars. Which, remember, they all looked the same blue in the first place. So the light from these farther stars has had to pass through a dusty molecular cloud and now looks redder. Meanwhile, the light from these stars hasn't, and so it still looks blue. So let me just show you a little bit more on what that looks like. So if here's our telescope, there's the cloud we're looking at. If we were able to view this from the side rather than looking directly at the cloud, then this is the picture that we would have. So remember, I picked stars that looked the same initially. So you can see that in reality, when we're looking from over here, we can see that all of these stars are blue. But the light from the blue star behind the clouds passes through the cloud, and that blue light gets scattered, and only the red light passes through. So the light from these stars looks redder, while the light from these stars still looks blue. Now, because we're looking at this in 2 dimensions again, when we look in the sky, we see something that looks like this. But by understanding the cause of this reddening and being able to measure the distances to the stars, we're able to tell where the molecular cloud is. And you can also see here that stars towards the center, the densest part of the molecular cloud, have had more reddening. So they're more red, even compared to these stars. And so by looking at how much apparent reddening stars at different distances have faced, we can figure out where molecular clouds are and roughly how dense they are. And we can do this across the entire sky. So remember, there are stars everywhere. So we can do this pretty easily everywhere. And when we do this in lots of different directions, we can actually make a 3-dimensional map of molecular clouds in the Milky Way. So here's what that looks like. Now, of course, I'm still showing you things in 2 dimensions because I don't have a 3D model here. But this image here is what you would see if, in principle, you could fly a spaceship hundreds of trillions of miles above the sun and look down on the galaxy. And what you see is a lot of interesting structure. So a lot of well-known molecular clouds, clouds that we've looked at like this since time immemorial, we now know where they are in space. And we can see that they're structured very interestingly. So here you can see this long linear feature that's called the Radcliffe wave. And it's a very, very important object in the universe, in the Milky Way galaxy. So people are studying this now for clues to how these molecular clouds formed and how star formation occurs. But you can also see many other structures that some are elongated. There's clumps of different molecular clouds together. And so by looking at the 3-dimensional positions of molecular clouds in the galaxy, we can start to understand how molecular clouds form. Now, you'll notice some other things in this map. So you'll notice that things look elongated, heading out from the sun. That's not real. That's a consequence of the way that we do this. And the measurements aren't perfect, and this phenomenon is well understood. So we're working on making better maps, and there's actually a new map that I'd like to show you that is of a smaller region around the sun. So again, the sun is at the center of this map. But here, you can see, by rotating here, the 3D structure of the clouds near us. And notice that there's not a uniform distribution here. There are many, many clumps, and you could see bubbles, so you could see this ring-like structure here that's real. And there are just a lot of really, really interesting things that you can see in this map. Very intricate structure that will tell us a lot about how molecular clouds form in the interstellar medium, again, leading to this picture of star and planet formation. So let me just dive in and talk about a couple really interesting structures. So this is something called the Perseus-Taurus shell. So Perseus and Taurus are two well-known molecular clouds. So this is what they look like in the sky to us. They look like they're right next to each other, with Perseus here, and Taurus more westerly. But now that we know the distances to these things, as well as all of the gas nearby them, we can see that they're actually both on the surface of a spherical bubble in the interstellar medium. So when stars that are very, very massive, much more massive than our sun, reach the end of their life cycle after just a few tens of millions of years, they explode. That's what a supernova is. You've probably heard of that before. And they release a lot of energy. And in this case, we actually think that between about 10 and 20 million years ago, something like 5 supernovae altogether went off and have caused a giant bubble to expand. And on the surface of this bubble, you get gas that gets compressed, and that's what leads to the formation of these molecular clouds. And it turns out that it's not just Perseus and Taurus. In fact, it seems that virtually all of the nearby molecular clouds are on the surface of an even bigger bubble that we call, rather unimaginatively, the local bubble. So the local bubble is an idea that's been around for decades, but we now actually have a definitive map that illustrates the geometry and extent of the local bubble. So there are two figures here, the one on both showing the local bubble. So the one on the left here has a bunch of arrows pointing out. Those are the motions of molecular clouds. So we measure how clouds are moving through space, and we see that in this giant cavity that we find in this three-dimensional map of the local galaxy, the clouds are not just on the surface of that, but they're actually expanding outwards. So this paints a picture of, similar to the Perseus-Taurus shell, expansion that causes molecular clouds to form. So you have an expanding bubble, and on the surface of that bubble, molecular clouds form. So the geometry and the motions of these clouds are all consistent with this picture. Then on the right, you can see that the Perseus-Taurus shell is actually meets the local bubble here. And so this cloud here, Taurus, is actually at the intersection of these two bubbles. So the gas there is being compressed in two directions. And so with that compression, you're able to get gas that's dense enough to form stars. So here's a direct quote from that Nature paper where these results were presented. Nearly all of the star-forming complexes in the solar vicinity lie on the surface of the local bubble, and their young stars show outward expansion, mainly perpendicular to the bubble's surface. Okay, so molecular clouds and many star-forming molecular clouds seem to be on the surface of expanding bubbles, where material is swept up and piled up on the shell of the bubble, which creates dense molecular clouds. But, like I said at the beginning, we want the complete story of star formation. So next, we can ask, what are these bubbles expanding into? So what is filling most of the space of the galaxy where there aren't already dense molecular clouds? This brings me to the diffuse interstellar medium, which is what I study. So, like I said earlier, the interstellar medium is what we call all of the gas and dust that exists between the stars and galaxies. The diffuse interstellar medium is the part of the interstellar medium that is much less dense than molecular clouds, but it fills a much larger volume than them as well. So it takes up a lot of space in the galaxy. So I'm going to tell you about how the diffuse interstellar medium sets the conditions for star and planet formation by being the very first stage of molecular cloud formation. So here, once again, is our multi-step process, our picture of star formation. So we start with molecular clouds, which then collapse in different ways under gravity to form stars. But even before this process begins, we start with diffuse gas that provides the raw materials for molecular clouds to form. Here's a snapshot from a simulation of gas in the interstellar medium. So you can see that there are some clumpy and dense structures here. So the more green or red the color, the more dense. And so these may be dense enough to go on to form molecular clouds. But the rest of this material is much less dense, and it's not likely to become star-forming molecular clouds. But it's still very interesting. And if, say, new stars form here, and there are some massive stars that form here and explode into supernova, then we'll get more expansion. And these supernovae will expand and sweep up this diffuse material. So, in putting together our picture of star formation, we really have to start in the diffuse interstellar medium, where all of this turbulent and interesting gas is providing the raw material for molecular clouds, and therefore star formation. So we're really starting to get to the very first stages of molecular cloud formation and star formation. So I'm going to talk about how we study this in two ways, using chemistry and dynamics. So the diffuse interstellar medium, which we usually just call the ISM, so if I say ISM, I'm talking about the interstellar medium. It's surprisingly chemically rich. So many models suggest that the ultraviolet radiation that permeates galaxies should actually destroy most of the molecules in the diffuse ISM. So remember, a molecule is just a collection of two or more atoms that are bound together. Now, ultraviolet radiation has this habit of breaking apart these binds until you're left with just atoms. So until you have something like a molecular cloud, which is dense enough to create a shield from the ultraviolet radiation to protect molecules deep inside the cloud from being broken apart, you're going to have this destruction of molecules, or so people thought. But there's not nearly as much shielding to protect molecules in the diffuse ISM, so it's thought that they should be mostly destroyed. But then when people, like myself, look out into interstellar space at the diffuse ISM, we find that molecules are much more abundant than expected. So I'll briefly tell you how we detect molecules in space, and then some results from work that I've been doing here in Wisconsin. So one of the best ways to detect molecules in the interstellar medium is by looking at absorption. So the way this works is that we have a background star or galaxy that produces a continuous spectrum of light. So you can think of that as something like this. So it produces colors across the entire spectrum of the rainbow here. So we see all of the colors of the rainbow. Now, when this light, this continuous spectrum of light, passes through a cloud in the interstellar medium, some of the light will be absorbed by that cloud. Crucially, only very specific colors of light are going to be absorbed. So this is because the atoms and molecules in the cloud all can only absorb these very specific colors. And every atom and molecule absorbs a different color from every other atom and molecule. So if we see what colors are absorbed from this continuous spectrum, then we can infer the composition of the cloud. So say, for example, I told you that nitrogen absorbs light at this wavelength here, at this yellow part of the spectrum. Well, when this light passes through the cloud here, we notice that that yellow light is gone. It's been absorbed by the cloud. So we can say that, okay, there's nitrogen in this cloud. But if I told you that magnesium absorbs red light, when this light passes through the cloud, we still see red light. So clearly there's little to no magnesium here because the absorption of magnesium is not present. So the light passes straight through. So there's no magnesium to absorb any of the light. So that's how absorption works and tells us what things are made of in space. I do essentially the same thing, but I do it using radio waves instead of visible light. So here's some of the telescopes we use, which are part of the ALMA array in Chile. And when we try to measure absorption at radio wavelengths, this is what we see. So we can think of the frequency of radio waves as being analogous to the different colors of light. And when we look at different frequencies, it's a bit like the dial on the radio in your car. So we can adjust the frequency. And just as different atoms and molecules absorbed light at different colors, they also absorb light at specific radio frequencies. So here we see that something is absorbing these radio waves at this particular frequency. And we know from physics what this something is. It's a particular molecule. So we can look also at the depth and the shape of this line to understand the quantity of molecular gas. So the deeper this line is, the more molecular gas we have. And the dynamics and turbulence of the gas, so how the gas is moving. So the wider this line is, the more turbulent the gas is. So here are some of our actual absorption spectra from sight lines in the diffuse interstellar medium. So clearly there's a cloud absorbing here. And actually, if you look carefully, there's actually two bumps here. That's because there's two clouds, two different clouds along the line of sight. And they're absorbing radio waves at their particular frequencies. And by looking at the frequency of radio waves that they absorb, so I've adjusted them here so they're all on the same scale, but by looking at the actual frequency they're absorbing, we can tell what molecules are present in the diffuse ISM. So here we see that there's HCO+. So this is a molecule that's very abundant in the ISM, even the diffuse ISM. So the amount of HCO+ is really nice to know because it directly is proportional to the total amount of molecular gas, whereas some other species only form in the densest molecular gas, and so they don't really tell us how much gas there is in total. So this is very useful for looking at diffuse environments. There's also HCN. One of many interesting things about this molecule is that it's thought to be one of the most important molecules in the origin of life. So its chemistry probably helped form the molecular precursors to living cells on Earth. And we're finding that it's very common out there in space. Then there's HCO. So this molecule traces the boundary between more diffuse and dense regions, so it tells us about the structure of the clouds. And then there's SiO. So this tells us where shock waves are present in the interstellar medium. So I'm going to come back to this one. So then, looking at different molecular species in the interstellar medium is useful because they all tell us different things about the interstellar environment. Okay, so now here, sorry about that. Here we're looking at a plot of the total quantity of molecular gas, which is what's on the y-axis. So higher up means more molecular gas, versus the total amount of gas along the line of sight. So that's on the x-axis. Now, I should have clarified earlier, by molecular gas, I mean gas that has molecules in it, obviously. But remember that molecules only form when the gas is cold and dense and well shielded enough. This is how we get the conditions for star formation to get underway. There's also, though, in galaxies, a lot of gas that's warmer and less dense, where only atoms can exist. So all of the molecules are destroyed and broken apart by ultraviolet radiation. So that's why the total gas is different than the amount of molecular gas. So I said that ultraviolet shielding destroys molecules in the ISM until there's an adequate amount of shielding to protect the molecular gas. So in this plot, we can see what an adequate amount of gas really means. So the colored points here show where we actually detect molecules in absorption. And then these gray points are where we don't detect anything. So there are no molecules present. So we can see that around this point, molecules start to form. And so this is telling us where molecule formation begins in the interstellar medium, setting the conditions for the chemistry and physics of giant molecular cloud formation, which will form stars and planets, as well as the chemistry that will also be important to the evolution of galaxies, as well as life. So with observations, we can see exactly where the first stages of molecular cloud formation, and therefore star formation, are happening in the interstellar medium. So we're finally getting to the very beginning of our story of star formation. So here's a threshold for where molecular gas starts to form. Okay, but it's not enough just to see where molecules form. We're scientists. We want to understand why they form there. So to do this, we use physics and chemistry to make predictions about how we think the interstellar medium should be, given our understanding of it. And if the models are right, then we can be somewhat confident, though not absolutely certain, that we have a good idea about what's actually going on. If, on the other hand, our models don't agree with observations, then we want to understand what it is that our models are missing. Why are we wrong, and how can we improve our understanding so that we're right, or at least more right, about our understanding of the interstellar medium. So this plot is a bit complicated, but I just want to explain it very briefly. So the x-axis tells us how deep the absorption of a particular kind of atom, actually just a hydrogen atom, is. So remember I told you the depth of this line tells us how much gas there is. So that's what's shown on the x-axis here. And the y-axis tells us the amount of a specific molecule, HCO+. So all of our observations here are shown in these colored points. Then there are these lines that are predictions from models. So on the left are predictions for the diffuse ISM, and on the right are predictions for very extreme ISM environments, like those around young giant stars. And the colors show the temperature of the gas, but don't worry too much about that. So we can see that for about half of our points, the position and the color of these points matches what the model says it should. So here, our diffuse ISM models are accurate. Okay, so there are some places in the ISM where our model does a good job of explaining what's going on. But for all of these other points, our predictions for the diffuse ISM are way off. So actually, these points are a lot closer to what you would expect around a young star-forming region, where there's a lot more dense gas and chemical reactions than you would expect in a diffuse ISM. We know that the diffuse ISM doesn't have these conditions. So the amount of molecular gas here is way higher than we expect. So there's clearly something missing with our models here. So let me just summarize where the research stands at this point. So there is a lot of molecular material in the diffuse ISM, including molecules that are important for life. We find a clear threshold for the amount of material required for molecule formation. So we know where molecule formation and then star formation really starts in the ISM. And we find that the amount of molecular material can't be explained with standard models. So, but we have to think of what's wrong. We have to come up with why the model is failing. So you see, I think we're onto the right track because one of the things that these models don't include is shocks. But astronomers are starting to recognize that shock waves in the interstellar medium are actually really important drivers of physics and chemistry. So I'll tell you more about shocks in a second, but I want to remind you that one of the molecules that we looked for was SiO, which is a special molecule because it's known to be produced only by shocks. So we actually didn't look for SiO initially. This came from follow-up observations that we were inspired to make because we wanted to test to see if we found SiO to see if we found evidence for shocks then in the environments where these non-shock models didn't match our observations. And indeed, we are finding evidence for shocks, and that we're finding that they're actually very common in the diffuse ISM. This is really important because it's going to tell us about the chemistry and physics of the diffuse ISM, which is, as I've mentioned many times, the seed of star formation. So, we're finding that SIO is actually between 10 and 1,000 times higher than expected without shocks. So, shock waves are permeating even the diffuse gas in the Milky Way. So the gas is shaken and stirred. This is really surprising because we're used to only seeing shocks in more extreme environments. So my job now is to understand what's driving these shock waves in the diffuse gas. So this is the kind of environment where we most commonly see shocks. So these lines show where SIO, that shock tracer, is found. So maybe you can tell this object at the center is actually, it's called a protostar, and it's ejecting large jets in opposite directions into the local medium. So these jets explosively launch out material. So here's an artist's conception of what that looks like. But like I said before, this is around a young star where we expect highly energized material to launch shock waves in the ISM. This is not the conditions we have in the diffuse gas. But we are finding that shocks are common in the diffuse gas, not just around these young stars. So we have to try to explain that. Now here, the image on the right is an actual image taken with a telescope showing you clouds with shock fronts moving through the ISM. And for comparison, on the left is a bullet moving through the air. You can see similar structure and for similar reason. So the clouds on the right and the bullet on the left are both moving fast enough that they create a shock front. So they're moving faster than the speed of sound. And they create a shock front. So the air or the gas at the front of the shock front gets compressed. And the compression allows dense and energetic chemical reactions to get underway. So this is what's required to form molecular species in the diffuse ISM. Unfortunately, it's usually too difficult or even impossible to make nice images like this one, which is why we have to look for SIO instead. So one issue is that we don't know exactly what causes all of the shocks in the diffuse ISM. So a popular and increasingly popular idea is that it is supersonic motions like this. So clouds in this, let's revisit this, clouds in this turbulent and diffuse ISM can be moving faster than the sound speed in this medium, which is rather slow, and create shock fronts, which then have enough density and heat to allow chemical reactions to proceed and provides enough shielding for those molecules to survive. But it could be other phenomenon as well. So one idea is turbulence dissipation, which I'll discuss shortly. It could also be clouds colliding together. So when clouds collide together, they can also form dense shock fronts. And in reality, it's actually probably some combination of these phenomena. But usually we can't get direct images of the clouds like this, and so we have to use SIO to understand where the shocks are. So this, like I said, is what we actually can observe. So we see the SIO on the bottom, and we compare it to the total amount of molecular gas, which remembers what HCO plus is telling us on the top. And we compare how much SIO there is per unit molecular gas, and it's really high, which unambiguously points to shocks. So this is what we actually have to work with. So anyway, I've been talking a lot about shocks in the diffuse ISM, but maybe you're wondering at this point, like, why should we even care? Why does it matter? Well, there are many reasons, but I'll focus on two. So one, I've already discussed, that's chemistry. So chemistry in the shock gas is very different than chemistry in quiescent gas. Densities are higher, and the shocks provide energy for chemical reactions. But the other is turbulence. So, as the name suggests, turbulence describes this like eddying and swirling motions of gas. And turbulence is hugely important to the ISM. So it releases energy on small scales, as we see here. So large scale driving, so things like the effects of spiral arms or galaxies colliding, it generates turbulence, which then cascades down to smaller and smaller scales until eventually this energy is dissipated and released in different forms. Like I said earlier, when this happens, the dissipation of turbulence can actually drive shocks in the diffuse ISM. But turbulence also provides support against gravitational collapse. So it's a lot harder to condense or collapse a cloud of turbulently moving gas than it is for just a quiescent gas sitting there. So understanding how shocks in the diffuse ISM drive turbulence and how this turbulence dissipation drives yet further shocks is important to know the initial conditions for star formation. So here I'm about to show you a simulation of the ISM. So you're going to see lots of wonderful things, including supernova explosions and star formation happening. So when star formation happens, you're going to see little dots. But here, I don't want to play the video quite yet because I want to just emphasize, here we are starting with some quantity of diffuse gas. And this gas, this initial condition, dictates how the entire simulation will evolve. And in reality, the initial conditions set in the diffuse ISM dictate how molecular cloud formation and star formation will take place. So this is the very beginning of this process, which is why it's so crucial that we understand it. So when we start here, these initial conditions tell us how this thing is going to evolve, and that's why we care so much about the diffuse ISM. So here we start, and then the gas, you can see a lot of turbulent mixing. You can see these giant explosions happening, so those are supernovae. You can see these little dots, those are all the stars forming in the simulation. And so you can see that there's this great motion of gas, and so some of the gas is released, and then it's reprocessed, and some of it will go back into star formation. And so there's this cyclic process, but it all starts with the diffuse ISM. And then you launch material back out into a more diffuse medium, and some of it will collapse after new stars form. So you can see that understanding how this begins and how it evolves really depends on understanding the diffuse ISM. Yeah, we have a question?
I'm just curious, that clip, what series of years did that occur that you just showed us?
Okay, so the question was, how long was the simulation running for?
Like in real time?
So actually in the top corner here, there's t equals, and that tells you how long it is. So we start at 0, and it runs, if we go towards the end, you can see it runs for about 650 to 700 million years.
Oh, so that's millions of years.
Yes.
That's a million years. Okay.
Yeah, so this runs for a few 100 million years. So you can see that this process goes over. And the Milky Way galaxy is something like 10 billion years old, or even older. And so this is just actually a small fraction of the history of the galaxy, even though it seems very large to us.
Thank you, that's very helpful.
You're welcome. Okay, so here is our emerging picture of star formation, which is a multi-scale and multifaceted area of research in astronomy. So star formation occurs in molecular clouds. Molecular clouds, it seems, form on the surface of bubbles generated by supernovae, which we can now prove thanks to 3D maps of the interstellar medium. And the turbulent and diffuse ISM is what sets the initial conditions for molecular cloud formation and for star formation then to occur. So here is the picture that we started with. We said we have stars. We know basically where these stars come from molecular clouds. And we said, okay, when we look out at the 3D structure of the galaxy, which we can now actually measure, we find that supernovae blowing giant bubbles into the ISM help condense gas onto the shell of these bubbles, which then produces molecular clouds that form stars like our sun. Apologies. We then said that this gas is expanding into a diffuse medium, and that this diffuse medium is shocked and turbulent. And understanding how shocked this material is and how turbulent the diffuse ISM is crucial, because this sets the stage for the rest of this to happen. So let me just remind you one last time why anybody should care. This tells us where we come from. So this essentially you can think of as us. So the sun and the earth and everything around us came from this process. So if we want to understand how this process works, where we came from, and potentially where other life in the universe might come from, then we have to understand physics all the way down to the diffuse ISM. So I've been listening to a lot of Stevie Nicks lately, and I think she had a really beautiful way of summarizing this picture. In her song Belladonna, she says, "Don't you know that the stars are a part of us?" So I'm not sure if this is exactly what she had in mind, but I'd like to think so, because it's true. The stars are a part of us, and we and the stars and everything else were born in the interstellar medium. So that's why we should care. So thank you all for coming and listening to my talk, and yeah, it's been fun.